Okay, so here we are at the SIMS. This is a dynamic secondary ion mass spectrometer. So what we're doing here is etching away some of the surface of a material so that we can get information about composition as a function of depth.
Okay, so what I'm doing now is just loading a piece of silicon onto the sample stage so that we can use that to evaluate the quality of the beam before we actually strike the samples with the beam, because SIMS is a destructive technique. We're actually making craters in samples, and so we want to do all the beam tuning on a piece that we don't care about, and that it has a pristine surface but is of no intrinsic value. And so we can see what the beam looks like before we actually put it on the samples and start doing damage. So Lewis is now going to put his samples down next to that one before we load them into the vacuum chamber. We have to maintain such a low pressure inside the SIMS analytical chamber that we tend to use copper clips to hold samples rather than bits of adhesive, which we might use in other techniques, adhesive tape. So it makes it a little bit more cumbersome loading, but it makes it easier to maintain the low vacuum that we need. Okay, so we can load those into the chamber. Got it? And pump intro. What we're doing now is just establishing the plasma from which we derive our oxygen beam. We're firing a beam of diatomic positively charged oxygen ions, O2+, mass 32, and that's going to be our primary ion beam. Secondary ion mass spectrometry, SIMS, we fire in a beam of primary ions, and that knocks ions out of the sample. Those are the secondary ions. They're the ones that we monitor with a mass spectrometer to get elemental composition as a function of depth. So we're rastering the beam at all times, we're eroding the sample away, and we are monitoring with a mass spec what is coming out of this hole that we're digging, basically. And so we get elemental composition as a function of depth. Okay, I think the pressure's down enough that we can load the sample into the main chamber now. It's been pumping down in the 4 chamber, which is a turbo-pumped chamber. This little chamber here is where the sample's been pumping down. And now we're going to move it into the main analytical chamber, which is ion pumped and sits at a much lower pressure. We're down in the -10 torr range in that chamber. So we're going to go ahead and introduce that now. You hear that big click, that door is open. So this gate valve is now open. So you're going to slide that in. Just slide it all the way until it hits the stop. Go through that far window. To begin with, at the beginning of a SIMS session, we need to know that we have a good beam. We need to have the beam compact, well-focused, well-shaped, so that we can make craters that have nice, sharply defined edges, so that later on when we gather our data, we know we're gathering it from a flat place within a well-defined crater. So we just can make a couple of marks on a piece of silicon here that we have loaded into the chamber. Right here is just an open piece of the silicon, and if I turn the beam on without rastering it, you see right here we're developing a hole that we're actually milling into the surface of the silicon. And if I raster that over a non-zero area, now I'm rastering it in a 200 micron width, and I'm making a crater. That white area you can see, I'm stripping away the surface of the silicon, and over time that will ultimately etch a deep rectangular crater into the surface. Zoom out and move over here to our actual sample, and this sample is a piece of gallium nitride that has been modified with some aluminum layers and some indium layers. The indium layers are there functioning as quantum wells, so I'm going to have a look at a non-zero scan here. And we're going to get a gallium signal first. This is gallium nitride, so we're going to see these white counts on the screen are actual ion counts of gallium. Not inherently
quantitative measurement technique, because in SIMS, as the name suggests, we are looking at the ions that are coming out of the sample. We are looking at, in this case, 24 plus Mg, positively charged magnesium ions coming out, and positively charged diatomic gallium coming out. Most of the elements coming out are leaving as uncharged atoms. But we can't detect neutrals. They don't leave any trace of themselves. So we're limited to detecting ions, which make a pulse on a counter. So in order to quantify how much of something there is in something else, how much boron you have in this piece of silicon, or how much magnesium you have in this piece of gallium nitride, you have to at some point run a standard. You have to implant a known amount of the element A into substrate B, and do a measurement of it and see what sort of counts you get from that. And then you're quantified in that sort of sample, with that sort of dopant and that sort of substrate. So here, where we have this very high sigma, we can calculate that we have about 1.3 times 10 to the 20 magnesium atoms per centimeter cubed in the gallium, which is something like 1%. This region, where it's clearly lower, we have about 3.5 times 10 to the 19 magnesium, still quite heavily doped. Now we've just hit the quantum well structure, and you can see the abrupt increase in 113, which again is a minor isotope of indium, and that is our indium nitride layer. That's our low dielectric, our low, rather band gap material that forms the quantum well structure, separated from another set of quantum well structures by this aluminum marker layer. So now our marker layer is coming up. This is also evidently a magnesium-doped region. And you see how the aluminum has, or the indium rather, has fallen. We can zoom in on that indium momentarily by going to a linear mode. Normally, we're looking at logarithmic scale here on the SIMS. Normally we do that because, again, SIMS is able to monitor things over many orders of magnitude. To increase depth resolution in SIMS is not just by going more slowly, although that's important, because if you go fast enough, you won't see all the features you're looking at. The machine is etching continuously as we go, and it's spending a certain amount of time looking at one element and a certain amount of time looking at another element. So if you go too fast, you will miss, you'll be looking at another element while there is a key change in another element that you're not watching. So you have to go slowly enough. But another point to make is that you can keep reducing the energy of your input beam. This beam that we're using today is a 2 kilovolt oxygen ion beam. The you bring the beam in, the less damage you're doing to the sample. You're not mixing it to as great a depth, because when you're doing SIMS, you're bringing in an ion beam into the sample this way. That means that the secondary ions that we're knocking out and monitoring are not the result of a single collision. You cannot physically bring a beam in and collide at this angle with a solid and end up knocking another atom, billiard ball style, out this way. It has to rely on a cascade of glancing collisions. And so there's a lot of damage involved in that. There's a certain amount of mixing that you do, and that inhibits your ability to get perfect depth resolution. But the more softly you can bring that beam in, the better. But the price you pay is that you also go more slowly, and then also the beam becomes a little bit harder to focus. And that is important also, because you want to have sharply defined edges on your crater relative to the width of the crater. Aluminum nitride, gallium aluminum nitride layers interleaved with indium nitride layers, or indium gallium nitride layers. The indium layers are the low band gap material, and the aluminum layers are the high band gap material. So you have this high band gap region sandwiching the low band gap regions, and that's what makes our two-dimensional confinement of our carriers, our electrons. Or in this case, probably holes, because we're dealing with p-type dopants.